So React is, you usually don't run React on a single node. It makes very, very little sense to do so. You could, but you would lose all of the fun that React offers, which is distributing your data for performance as well as for failover. So what we do, we use the SHA-1 key space, so 160 bits, and then we create a ring. So we evenly divide this by the number of actual nodes. When I say nodes, I mean physical nodes. The way we get around this is when this changes, we actually assign everything a virtual node, and then we change the size of how many virtual nodes are assigned to a physical node. So that's why we can actually divide it like that. So here's how it looks. So when you write data, your typical value for replication is 3. We recommend that. We recommend you start off with at least 5 nodes. Anything less, you're not really building it for failover, which is one of our strong suits. So if you aren't doing that, you can totally get away with having a different end value, but you're going to trade off your actual data consistency. So in a disaster, a node fails. So your data has already been distributed to 3 different nodes. It is able to, when you go to a node, it's able to know where the other data is at any given point in time. When it does fail, the request will go to the fallbacks. The data will actually hand off to other nodes, and then as soon as it comes back online, the data will redistribute automatically. There's no, this is built into the system. There's no, you don't have to tell it, oh, this node has failed. It will figure that out automatically. Some of the features that we offer, MapReduce, full text search, it's Solr-like, and I'll actually touch on this later because we have a new backend that is coming that will make it fully Solr-like, and secondary indices. The secondary indices are only available with the LevelDB backend, which is our 3 backends. LevelDB is the Google backend, if anyone's ever familiar with Bigtable. Google uses that. It stores files on disk in SSTs. I can't remember what SST stands for right now. That gives you secondary indexes. It's great when you can't fit your key space into memory. So you are going to have to write to disk. You're going to have to touch disk. It's great at that. It does compact, like a lot of the other solutions for distributed databases. So you have the reason it's called levels, you have multiple levels of data. So if you do have to search through every single level of data, you're going to be doing a lot of seeks. So FastDis and LevelDB like each other a lot. Bitcask is what we actually have developed ourselves. Bitcask is just a simple log appended. You don't get secondary indices, but it's very, very fast. High throughput. And then there's a memory backend. I wouldn't suggest that anyone use it outside of testing because it's just, it's just in memory. So if you die, you die. It's not very good. New in 1.2. I only include these because a lot of these were features that were asked for a long, long time. Used to be when you had joined a node to a cluster, you just join it, and it just immediately jumped on. Well, if you're adding, say, 10 nodes to a cluster of 50, that's a lot of network traffic. And a lot of people were complaining because they don't necessarily have 10 gig E on the back end, and that would just crush their networks. So what we've done is we've done basically it's kind of like a SVN, you stage a commit, and then you can stage a commit at any time, and you can set a cron job or something to actually commit it later. That makes the load on the network go by a lot easier. It also means that if you have a plan that you've set up that you don't want to go with, you just clear it. Capability negotiation used to be you had to run the exact same version of React, so rolling upgrades were a pain. Now we actually have a feature where you can have mixed versions, no problems. It will negotiate capabilities so that if you have a feature that is, say, added in 1.3, it won't break. It'll drop down to the lowest common denominator. Better handoff visibility. This was a key thing. A lot of people want to know where the handoffs are happening. And just because they see giant spikes in network traffic and want to confirm that things are actually passing from one node to the other correctly. This is a big one. I'll touch on this. The repair KV and search via console used to be, so we do read repair. So value's out of date on a node, you repair it on read. The problem is if you have a lot of data that's say that it's not right, there wasn't an easy way to go in and repair all of the values. That's something we've added in the latest version. Stats, it's a boring one. For those who are big fans of FreeBSD and SmartOS, we added official packages. And then the big ones, EDS, SSL built in. We used to use like stud or something in front of it. And then granular controls. The problem we were having with multi-data center replication is the sheer quantity of data shifting, going over the going over the pipe. So we now have both real-time and full sync. There are a lot of customers who don't necessarily want all of their data passing over their WAN interface constantly. And this is the one I want to talk about. So when I said we do have full text search, it's not really like Solar. This is Solar. So Yokozuna is our new backend. It's coming soon. I'll bug Ryan to make it come sooner. But it's basically, this installs a Solar instance on right next to every React instance on every node. Cool thing about this is you get full Solar compatibility. Anything you can do in Solar, you can do with Yokozuna. The nice thing is, instead of being multiple instances on the Solar side, it's all, you just query one, and then React does the distribution. It still works like a distributed query, works very quickly. And I would show you, we actually have this live on our documentation site right now. I don't have Wi-Fi, so you can't. But the bonus here is we also have active anti-entropy. This means that instead of having to do, as I mentioned earlier with doing read repair, this is constantly going through and repairing values. So you can delete something and it'll just know, once an exchange has happened between two nodes, it realizes that something's changed. It's fixed. Then CS. So React CS is basically an S3 compatible storage engine that runs on top of React. It does almost everything that S3 can do. I'm not going to say it can do everything that S3 can do because we still can't do a few bits, but it's very, very, very fast. It gives you all the fun things you get from S3. You get multi-tenancy, multi-billing, so you can look at individual customer usage. This has been a big request from enterprise customers. They really like to be able to use this just for different departments inside their own organization. And this is how it works. Basically, React CS is just a very thin layer that then sits on top of React. So it uses multiple backends on React, but it's just a small Erlang process. So typically, you run React CS right on top of React on the same node. You could run it on different nodes, but it doesn't make sense for the performance. So DevOps. This is what I do. Our role at Basho is to make things easier for everyone to install. A lot of the problems we have with folks when we give them React is that first Erlang, they're befuddled by the configuration files, running it locally. It gets very messy. So a lot of the work that we have done on the DevOps side has been making it easier to use. This is through Chef cookbooks, Puppet, I can't even remember, Puppet recipes, I think they're called. I'm going to demo the React Dev cluster, which is a Ruby client written by our friends at Zing, or a Rake system written by them. That makes it really easy to spin up a local cluster for testing. Because that's the biggest problem, is getting people to download and compile Erlang, getting all the dependencies set up, and then, oh, well, you're on OS 10.7, you need this particular GCC. Hardware recommendations, that's something we've been working on recently. A lot of our customers have pushed us to the point where we can't actually test their scale. They have 50, 100 nodes, and that's not easy to do if you don't have 50 to 100 nodes. And some of these customers have insane specs for machines, like maybe 8,000-pound machines that are all SSDs and 24 cores. So what we do is we've been testing on customer setups, and then we basically break React a lot. That's what we do. We set up test harnesses where we constantly pound it with our Basho bench tool. And then once we find these edge cases, we pass them off to AppDev and we say, here, we found a new way that it's broken. So that's what we've been doing a lot recently, is breaking React and React CS, and then those enhancements have been rolled into the product. There are actually 3 or 4 releases that have been made in the past 2 months that have just been from DevOps recommendations, where we've seen break, and this is, again, scales of 50 to 100 nodes. What we've learned, Linux kernel is really, really bad defaults for high performance. It's basically designed for the lowest common. It's basically designed for an i386. That's really bad when you have a database that's pushed, it's able to saturate your network and your disk subsystems. So don't ever use the Linux kernel defaults with React. It's a bad idea. So some of the things we found, most of the TCP settings in the kernel, far too conservative. We're typically running React on real physical hardware. You can run it in something like EC2, but the latency that you get in a kind of distributed, or not distributed, but a virtualized system like that, there are no guarantees. So we prefer low latency, 10 gigabit, high throughput networks. So you can tune TCP a lot. The PD flush that I mentioned there, dirty pages, Linux kernel is not optimized for high throughput for that. Also, it expects swap for everything. You're not going to swap if you have 32 gigs of RAM, or you shouldn't be swapping. So that VM swappiness value is set to it's set to 60 by default. You drop that down to 0, you never want the kernel to think they can swap. Sir, you probably want to have some swap there because a lot of applications die if you don't have swap, but you never want to be touching that. I/O schedulers, terrible. The default scheduler in kernel 2.6 and above is CFQ. I've done my cute little completely flawed queuing. It's supposed to be fair. There's a deadline scheduler and a no-op scheduler. We've seen performance improvements of about 200% when we change the schedulers. It's really that bad. It's basically trying to say, oh, I'm going to fairly schedule every single process on the machine. Typically on these machines, you're only running one process, and that's React. That's something we've noticed. That's a lot of customers. They're like, oh, I'm getting terrible performance. I'm maybe only getting 10,000 ops. Change the scheduler, 50,000, 80,000, very easily. Hardware load balancers aren't really as great as they're cracked up to be. We run HAPoxy locally on each React instance. That way, if any node goes down, it's already aware of the other nodes in the cluster. That actually is a very small performance hit, and it's a lot more flexible than running hardware load balancers where you have that hardware load balancer being a single point of failure. And Bash.Bench is our open source tool that we use to benchmark React. It can be used to benchmark any kind of key value store. It's written in Erlang, and you have a bunch of different options for all the backends. And I was going to show this off, but this is, if anyone was curious and playing with React, we actually have a live demo that's running in our data center. It's multi-tenant, so anyone can sign up. You just put in, you can actually just go to the site and request a login, and then our sales team gives them out and ask you how you're doing. But I did want to show this because they're pretty graphs and things. That's the end of my presentation, or my part of the presentation, but I wanted to show everyone our, it needs to be way bigger. This is, let's see, it's bigger. There we go. So we have this little rake tool. So this, if you want to set up React really quickly on your local system, just do I've already done a rake install, but if I wanted to start up a new cluster, a 5-node cluster, this is also for OS 10 specifically, so if you're not running OS 10, it's pretty easy to do it on a Linux box, but you have to, again, know how to compile Erlang. Some of the other bits. But this will show you what React actually looks like. Take a second for this all to join. Oops. So what this will do, this is actually going through, joining each of the individual nodes to the first node. You don't have to join any specific node to any other node in any specific order. Once it's part of the ring, you can join any node to any other node and it knows what it's doing. So this is React control. This is a nice little web interface that you can very easily see the status of your cluster. So big green check mark if you're running low on memory, or if a node is dropped out, it's a big red X. But here is the fun part. So here you actually see the actual distribution of partitions, and this will actually change as these nodes, oops, I'll just reload that page. So as you see, these numbers will actually change live, and these are the V nodes, or partitions, that are being distributed between each of the individual nodes. So if I were to kill one of these right now, so it'll read that as an error. That node's gone down, but then the numbers will actually change and redistribute as it recognizes that that node is down. Like I said, this is all based on an n value of 3, which is why we recommend you have 5 nodes. So if you have 3 copies of your data, 5 nodes, you've got it spread around so you can suffer failure and the performance hit a lot easier. And that's all I have, and I was going to pass it over to Chris.
Yeah. All right, as Seth mentioned, I'm part of the client services team at Basho and Mia. So the London office has been around for about 6 months now. I've been with Basho for about 4 months. And I wanted to take a different approach to this presentation. I thought I could make it a little bit more interactive and basically hand it back over to you. I mean, I would like to ask, has anyone actually experimented with React before this talk? No one else has experimented with React. Okay. To explain how you could get started and get working with React, typically, as was mentioned, I think with the Cassandra talk, Cassandra has a query language. React speaks just HTTP REST direct. It was built from the ground up to speak through a REST interface. Recently, in a couple of versions ago now, it's been quite stable for quite a long time now, we introduced a protocol buffers transport layer as well. So all of our official client libraries and many of our community-supported client libraries can talk both the HTTP interface and the protocol buffers transport interface. Okay, and that in a production environment, we pretty much recommend that you use the protocol buffers interface because the HTTP header overhead and some of the conditions that go into being a faithful implementation of the HTTP protocol specification means that there's a little bit more overhead than there should be to respond to your requests. So if you want to be in a production environment, in whatever implementation language your application layer is being developed in, whether it's Java, Python, Ruby, C#, whatever, typically when you switch, you could do a lot of easy development in HTTP, and then when you want to switch to production, you can easily switch the knob over to protocol buffers, and you'll get that performance improvement. There's a lot of scenarios where people go, well, what is React's sweet spot? When should I use React? When should I not use React? And we like to just, like at Basho, we do our own benchmarks, we do our own performance tuning, and we try to keep as open as we can to all of the research work and all the developments going on in the other databases. That's extremely hard to do because things like RethinkDB, I don't know if you guys are aware of that, just recently was announced about 2 weeks ago that it was a re-announcement of a product that was being developed a few years ago. So the NoSQL database landscape continues to grow at a alarming rate. Okay, so I haven't had a chance to do any analysis of RethinkDB. I don't know where their sweet spot is yet in the market, so please don't ask me anything about Rethink. But with React, typically, this is going to sound extremely obvious, but if you can denormalize as much as possible, you can do a pure KV lookup, that is going to be our sweet spot. Things like user profiles. We've got a lot of companies like Rovio and Riot Games who are customers of ours, and what they do is they use React to store user session data, so game session state. And that's a beautiful KV story because you know the user's ID, so you can use that as your key to your records. Okay, you can denormalize as much as possible, and it's one request, and you can retrieve in one lookup everything you need for their latest game session. Other use cases, I've found a lot of interest recently from people developing content addressable storage solutions. And I like this one because it's a mashup of taking advantage of the fact that React.cs, our cloud storage platform, sits as a thick proxy just right on top of your React cluster. Okay, so really what you get when you pay for the enterprise product is you get that thick proxy to handle distributing and dividing up those file objects into blocks that we can then store to disk and replicate for data redundancy and availability. But with the content addressable storage solution, what you can do is you can store file metadata information and user account information into the underlying React storage engine, but then still access through the S3 layer for your actual files. So we've got people building their Dropbox style clones, so things like some sort of daemon process, maybe in Python or Java or whatever, sitting on a customer's machine or in one of their business units data centers, going and constantly kind of calling out to the React under the CS layer of React core product, going in, talking to that, getting a file listing, getting a listing of all the S3 file handles that you need to pull those files back out and store them a local copy. And that happens as a synchronous process, asynchronous process to pull that data as fast as possible and keep it in sync the way that Dropbox, and if you're aware of their storage solution, how they do that. So a lot of customers are using that at the moment. What I would always recommend when deciding whether or not React is a sweet spot for your use case is think about your query patterns, okay? It seems obvious, but some databases like Cassandra are, as was mentioned, write optimized. React is pretty much agnostic to that. It will let you read as fast as it will let you write, you know, and you're really constrained by whatever your disk subsystem is allowing you to write to disk, okay? We don't do buffering in memory to kind of bolt together, block load these writes and then push them to disk. We write as fast as you let us write to disk, basically, based on the hardware spec that you've got. You can do some neat things with that. I can't remember who it was at the front who asked about that, but asked about SSDs and optimizing with SSDs, right? What you can do if you don't necessarily need to ever solve the problem that you're talking about at the database layer. You could actually do the same thing with Cassandra. You can basically take ZFS, we're big fans of ZFS, it's a great file system that allows you to use an SSD as a kind of what they call an L2 arc cache. Think of it as a extension to your RAM. That can maintain your hot data set, and then obviously everything else is auto-managed by the ZFS subsystem to actually make sure that it's on the spin disks that are in the rest of your storage layer. That's really nice, because then you can keep it cost effective. You get an SSD, a modest size SSD, that almost bumps up your RAM count basically, and then you can use cheap spin disks to actually store the data for as many years as you want to store it for. So we find that that's something that I typically recommend, because I spend a lot of my time doing a combination of data modeling, trying to help people find the correct balance between when should I be using secondary indexes, when is link walking appropriate, how does this work under the hood, should I be doing map reduce operations, what's the key set size that I could really do efficiently within React, you know, how bounded is that access for, say, real-time analytics. Typically, these problems can all be solved by pulling them away from the request chain that comes in from your application layer. So let's say that you're building a mobile app, and your mobile app has to sustain, I've seen people talking about kind of 30,000 ops per second across a modest cluster running in EC2, not the greatest hardware. It's possible, but what you want to do is not be doing map reduce operations linked to every single one of those requests that are hitting 1,000 keys on your cluster. You're not going to get the throughput and the latencies that you're looking for. You will be constrained at that stage. So what you can do is work around that by basically, for a time series use case, for example, you take time boxes, so you pick sort of time increments that you want to box up into some sort of what we call buckets in React, just logical namespaces for your keys, and then roll them up as a background process, and do background processing to actually take the map reduce across that key set, and then fold that into what is a single record that then gets pushed into your 1 minute bucket or your 1 hour bucket, and you can almost end up using the system to do roll-ups like that, and that allows you to do everything you could do with the analytics that you need to do without really worrying about, do I need to attach this request chain, this heavy read or write throughput that I'm pushing through my system directly into the cluster and have it service them all in one go. You know, write it into a bucket, let a background process go in, and then fold that, you know, reduce that result set and then store it again to another bucket. One of our customers, Boundary, they've got a network daemon that goes on servers and then will stream information about kind of network latencies and other kind of network topology information. Each of those daemons is attached on a computer and accesses a React cluster in their infrastructure. But they don't do a map reduce operation when they're doing their analytics to display their graphs to customers. They don't attach that to their request chain. They use time boxes and then roll it up. So the problem when you compare, then this is something I come across quite often, it's impossible really to compare relational databases to these schemaless designs, because you're talking about different trade-offs and different throughput and different latencies. So once you understand that, you have to start thinking about your data model in a lot more detail than you would have done before. I mean, I was a little bit late to this event because I was in a meeting earlier. And in the meeting we were talking about how can we put together a handbook, and in that handbook describe typical patterns for a relational mindset to move into a React denormalized KV mindset. I'm not a fan of that process, because that process is trying to offload the thought patterns that go into actually caring about how to model the data problem into something that can be turned into a learn-by-rote approach. There's too many variables to account for to get the kind of efficiency that we're looking for these days, and the right throughput and volume of access that we need in a highly available system. The reason I asked so much actually about distributed counters earlier is because it's an extremely hard problem to solve, and Cassandra have an interesting implementation. It's a lot of work that we're doing at the moment, and one of our research projects is into commutative resolvable data types. And these data types allow you to, basically they're a particular subset of all data types, of abstract data types. They can be known to be monotonic structures, which means they're known to grow in size. Okay, so for instance, if you take the set union of two sets, where you know these sets are never going to be reduced, then you can just do the set union operation, and then you'll have your complete record set when you're doing some sort of conflict resolution on concurrent writes. This kind of research is very interesting stuff. It's an extremely hard problem to solve in a distributed system, and especially if you don't want to introduce locks of any kind or some sort of transaction mechanism. But we're doing a lot of research into that, and one of the things that Seth mentioned was I'll work in Yokozuna for search. That takes advantage of previous research we've done with this active anti-entropy technology, which is one of the areas where it was possible for you to lose data in previous versions of React. This is pre 1.0, was that you could basically, React would do read repair when you next read the value, right? So if you have replicas of that data, when you do a read, it will go and it will request all of the replicas and then verify whether there's stale data that needs to be updated with the current primary copies of that data. Okay? But if those stale keys haven't been read for a long time, and that node has been downed and come back online, it could well be that at some other stage in time, another node in your system goes down that has the other primary copy, and then another one. And all these happen at different time periods, but happen before the next read of that key has happened. So what has actually happened is that you've now got 3 stale copies of that data, and you're unable to determine which one is the most up-to-date copy, and therefore push that consistency back up, which is what the read repair operation does. Active anti-entropy is, think of it as a background process, which constantly, actually the new structure we use for storing on disk makes this much more efficient, but it accesses these vnodes and accesses the data partitions and determines, has anything changed here? If it has, let me make sure I run read repair and push this consistency up. And that no longer has to happen on every request, on every read. This happens as a background process. And that work is going into our 1.3 release, which should be December, January time.
Yeah, I'll say Christmas time.
Yeah, yeah. Let's hope it's a Christmas gift, right? And that will, that paves the way for work with Yokozuna, which again is this direct integration between the JVM and the Erlang VM, so that we can control and spin up JVM instances alongside the Erlang VM and allow it to be auto-managed, allow you to define indexes that you want to be searchable and copied across into your Lucene and Solr indexing, so you can do distributed queries over that data. Yeah, I wonder if anyone has any questions. Is there anything you'd like to know about React versus Cassandra, maybe? I have that question a lot. We have different sweet spots. At this stage in time, if you want to do distributed counters or you want to do time series data, then I would still say go with Cassandra. But if you want to do denormalized pure KV lookups and you want to make sure that you can scale, because as far as I'm aware, correct me if I'm wrong, but the vnode implementation in Cassandra is not, it's in master I think, but hasn't yet been resolved alongside rack awareness. So scale factoring in Cassandra means either manually recalculating your vnode distribution or scaling a factor of 2. So you can evenly divide your data blocks and then distribute them across your new nodes. So we have different sweet spots. You can do time series in React, like I said, Boundary do it, but it requires a lot more thought into your data model, where an environment like Cassandra, which gives you this ability to do partial updates because of their column family orientated database, will give them an edge in time series problems. Yeah, so if you want to store game session data, you want to do time series like Boundary does with their analytics platform, or content addressable storage, or anything that can be denormalized into a pure KV problem, then you want fast reads or fast writes. Yeah, do you have any questions?
Yeah. So I'm quite interested by the thing you mentioned is sound a bit like MapReduce kind of pattern.
Okay.
So you're saying put it into a bucket.
Yeah.
And then have another MapReduce on that.
Well, yeah. Put the value basically as with any of these schemaless database engines. You really need to think about what is going to be your index. What's going to be your key. Right, and in the time series problem, your key is going to be something and some sort of time stamp of some kind, right? So if you can put those keys into a particular bucket, a logical namespace like you would in React, then you can store 70, 80, 90, 100 ticks in there. And after your tick count has reached a certain failover in time, you pick up another bucket. And then your background process sweeps through, does a MapReduce operation over that bucket, which is now a closed-off time box, so you know no more records are going to be pushed into that bucket. You can then flatten that into one record, push it back into React. That's how Boundary do it.
Is that part of? It's not part of React, obviously. Is it part of something you do?
It's I do a lot of data modeling work with people that want to use React, whether it's open source on the mailing list or whether it later becomes enterprise stuff. And a lot of that becomes, talking about how we can think differently about storing that data. And that time boxing process, you would have to build, we've got Erlang MapReduce phases that you can, pre-built operations that you can then use to do that time box reduce. But the actual process of taking your application layer logic to push it and logically namespacing that time would be a problem that you'd solve in the application layer. So there's no pre-built solution for React, but there's a lot of people that are doing it, and the mailing list is full of people that could help in explaining, myself included, the best way to go forwards with it. Yeah. Cool. Any questions? No.